So I will continue the construction of Calabi-Yau compactification of heterotic string today, and then go on to discuss other objects we can consider in string theory, and we'll start with D-blend. Okay, so we are considering E8 cross E8 heterotic string. On Calabi-Yau manifold, and supersymmetry. So if we require at least minimum amount of supersymmetry for this compactification, then it requires that there is some covariantly constant spinor. Well, for H is non-zero, not exactly covariantly constant, but a condition is that the derivative of epsilon and H contracted with gamma matrices vanishes. So in particular, if H is equal to 0, then epsilon is covariantly constant. And so here is Diratino, and so again, H contracted with gamma matrices appropriately, and this should vanish. And then Gaugino have this condition. Okay, so these are supersymmetry conditions. And in addition, there is an equation of motion. Okay, so for this lecture, we have been considering this particular type of solution for which the three form vanishes. So we impose this condition. So this is called 2-2 compactification for the reason that, well, this by itself is not a 2-2 compactification. Let me clarify. So if H is equal to 0, so first let's consider H is equal to 0. Then, so if you impose this condition and impose some additional condition, it becomes one which is called 2-2 compactification. But let's first think about the consequence of H equals 0. So if you require H equals 0, then it means that there is some epsilon so that del mu of epsilon is equal to 0. And as we discussed earlier in this lecture, this leads naturally to the condition that if the 10 dimension is compactified to some 6-dimensional manifold times flat Minkowski space, then M6 is a Calabi-Yau manifold. Okay, so this is one condition. And another condition is that del bar of phi epsilon is equal to 0. So that means that the phi is constant. And then from the third equation, we see that f slash epsilon is equal to 0. So this equation turns out to be the condition that Gij bar, Fij bar is equal to 0. Okay. So Calabi-Yau has this rich flat scalar metric. So it's a complex manifold, so we can use complex coordinate, and the metric can be written in this way, with some scalar potential k, and where I and j go from 1 to 3. And this condition implies this condition. This is actually higher dimensional generalization of self-dual equation. So in 4 dimension, we have this famous self-dual equation for gauge field. Plus or minus f mu nu. So I think we might need 1/2 here. But anyway, so we have this kind of equation. And this equation implies if F is expressed in terms of gauge potential, then this equation also this equation implies equation of motion, because this equation in the language of form is equivalent to say that F is equal to plus or minus star F, and Yang-Mills equation is D plus A which F is equal to 0, and star of this is equal to 0, and this is the Bianchi identity. So this follows from the equation, the definition of F, that this is equal to A squared. So this automatically implies this, and so if F is equal to F star, this is also satisfied. So therefore this implies equation of motion. So this is actually, but of course this equation is stronger than equation of motion. So this gives you a special class of solution to Yang-Mills equation. So this is called self-dual equation. This is a generalization of this equation to higher dimension in the following sense, that in 4 dimension, if for example your 4-dimensional space is scalar manifold, then this equation can also be written in this way. So in that sense, this is actually a higher dimension generalization of self-dual equation. Okay? So this is an interesting class of F. So these are the 3 conditions. Calabi-Yau, the Dilaton constant, and gauge field is generalization of self-dual equation. So this is called actually Uhlenbeck-Yau equation. Now, there is one more condition, which is that now with this equation motion for H, Bianchi identity for H, I should have said, if H is set equal to 0, then if H is equal to 0, so if H is set equal to 0, then it also implies that the trace of R which R mine is equal to trace of F which F. So a special solution corresponds to the choice that omega, the spin connection, is equal to A, the gauge field. So this is the E8 gauge field. Okay, and so if you impose this condition, this leads to what's called 2-2 compactification. It's called 2-2 because for this particular type of compactification, the worldsheet theory in the Nouveau-Schwarz-Ramond formalism can be described in terms of superconformal theory with n equal to superconformal symmetry on the left and n equal to superconformal field theory on the right. So that's why it's called 2-2 compactification. There are more general class of solutions to this equation where you can solve the equation that R wedge R is equal to F wedge F, or more generally R wedge R minus F minus F is in a trivial cohomology class, but still satisfies this equation, in which case you are deviating this from this equation condition. In that case, the supersymmetry on the side where gauge field is coupled to, typically the right mover, has no supersymmetry on the worldsheet. So those are called, so you can have a solution where omega is not equal to A, but a trace of R wedge R is equal to trace of F wedge F. And these are called 2-0 compactification. So the space of 2-2 compactification is very well understood. It's essentially the moduli space of Calabi-Yau manifold. So that's very nice, beautiful geometric construction. The space of 2-0 compactification is more difficult, and the entirety of class of solution is still to be understood. So for this lecture, for this course, I will focus on this simpler setup. Now, if we impose omega is equal to A by the Calabi-Yau condition, and therefore omega satisfies certain equation due to the Calabi-Yau condition because omega is spin connection, so it's determined by the Calabi-Yau geometry. Then from that, actually, this equation is automatically implied. So combining all these, what this means is that if the manifold, 6-dimensional manifold M6 is Calabi-Yau, and if you set omega is equal to A, then you have a supersymmetric solution for the E8 cross E8 heterotic string. And so this will give exact solution to three-level string equation motion. Okay, so now we're going to consider this, and then 9 plus 1 dimensional space-time is compactified to 4-dimensional space-time with internal Calabi-Yau. So then you can ask what are the massless particles? What are the content of massless particles in 4 dimensions? So this is what I would like to analyze now. Okay, so it's E8 cross E8 heterotic string, so gauge symmetry. In original 9 dimension is E8 cross E8. But by compactifying on Calabi-Yau 3, this one of the E8 is decomposed into E6 times SU3, and SU3 part is broken by the fact that omega takes value in SU3. So it's like Higgs mechanism, that background breaks the symmetry. Okay, so therefore this is a gauge group. This is a gauge symmetry. In 4 dimensions. So therefore, when we consider a spectrum of massless particles in 4 dimensions, they all fall into the multiplet of E8 cross, please excuse me, E8 cross E6 representation. In general, if you consider the entire tower of heterotic string particles, physical particles in the heterotic string theory in 10 dimensions, they are representation of both E8 and two E8, this E8 and this E8. But for the massless sector, it's either representation of one of the E8 or the other, because massless particles charged with respect to E8 cross E8 are the adjoint representation of E8 cross E8. And so if you have a tensor product of a gauge group, then the adjoint representation of that group is the sum of adjoint representation of E8 cross E8. So it's either a representation of this E8 or this E8, and not both. Okay? So therefore, we can consider a decomposition of representations for each one of them separately. So in the case of this E6, well, we can have adjoint representation, which is in 78-dimensional representation, or we can have chiral fermions in 27 representation, or its conjugate. The other E8, so let's call this E8 tilde. It's not like you have a group called E8 tilde, but just to distinguish this from this E8, let's call this E8. So these are all neutral with respect to this E6. So these are the candidates for dark matter. Because these are not sensitive to this E6 gauge symmetry. Okay, so now let's see what kind of particle content you have for this E6 sector. So for this, it's useful to understand the decomposition of representation of E8 into this in more detail. So in 10 dimension, we have a gauge field. So we are considering n equal 1 supergravity in 10 dimension. So we have n equal 1 supergravity multiplets, which are in singlet of E8. And then another thing is n equal 1 super-Yang theory. So in 10 dimensions, so let me write it out explicitly. In 10 dimensions, we have n equal 1 supergravity. So these are singlets of E8. This does not transform non-trivially under gauge symmetry. Plus n equal 1 super-Yang, which is in adjoint of E8. And so therefore it is the representation of 248. So you have a 248 dimensional representation. It was important that this dimension is 248 for the anomaly cancellation. So therefore, if you are interested in massless particle in 4 dimensions, transforming under this type of representation, we should focus on decomposition of this representation. Okay, so this is, so you can look at the table of, so you can look at the Encyclopedia of Mathematics, for example, and see how E8 248 get decomposed into the product of representation in E6 and SU3. So the decomposition goes like the following. So 78,1 plus 1,8 plus 230, plus 27, 3 plus 27 bar, 3 bar. So this is the decomposition where the first one corresponds to representation of E6 and this one is a representation of SU3. So the way you read it is that the first item is the singlet under SU3, but is adjoint representation of E6. And it's natural because you start with adjoint representation of E8. So if you decompose that into representation of E6 and SU3, there are two things that should obviously come in. One is the singlet of SU3 and adjoint in E6. So you should certainly have it because you are decomposing the adjoint representation into subgroups. But you should also have adjoint representation of SU3 and singlet of E6. So that's this one. And then there are two mixed ones here. So this is, if you like, it's like fundamental representation of SU3 and the fundamental representation of E6 and their conjugate. So it's very natural because typically adjoint representation is a combination of fundamental representation and its conjugate. So therefore, the decomposition naturally falls into adjoint representation of E6 and singlet, or singlet and adjoint representation of SU3, and then product of fundamental representation of the both things. So this is how decomposition works. And if you do the math, then you see that they are done. Okay. So now you can ask, well, how? So what are the some of these things? So first of all, this is easy to understand. So these give rise to n equal 1 super-Yang mirrors with gauge group E6 in 4 dimensions. So in 4 dimensions you have supersymmetric gauge theory with E6 gauge. Okay? So now let's skip this for now. I will come back to this one. Let's look at these things. So what is this 27? 3. Okay, so this is in the fundamental representation of E6. So you can think of this as some kind of matter field. So you can ask, so these are n equal 1 chiral multiplet. So this consists of chiral fermion and its super partner, scalar partner. Okay? So then you can ask, well, how many of these appears? Okay? So this one, there is only one multiplet, but in general, there can be several of this multiplet, and it's important to count how many there are. Okay? But these three correspond to SU3. And this SU3 is actually the transformation property of this spin connection. And this transforms in the same way as these three coordinate indices. Basically, the tangent space to the Calabi-Yau manifold transforms as a fundamental of SU3. So therefore, if you have three, then what you should do is to think of this as some kind of field which transforms as so let me write it out. So yes, so what you start with is in 10 dimension. In 10 dimension, you have gauge field which transforms as E8 adjoint, and then you have a space-time vector. So this was a 10-dimensional gauge field, and it gets decomposed into this way. Okay, so now what's going to happen? So in this sector, what you have is an AI. So the I comes from space-time vector in 10 dimension. Part of that is 4 dimension. And then, but I is now pair of 27 and 3. So that means that you can write this as A and J, where A is the 27 representation of E6, and I is SU3, the fundamental representation of SU3. But this is also the same nature. This is 3 of SU3, because it comes from the space-time vector. So therefore, the field that transforms in this way can be thought of as a bivector on Calabi-Yau manifold, both holomorphic indices transforming like 27 of E6. Okay? And so what is this? Well, so if you have AI, J, I and J does not have a particular symmetry property. So it's not easy to, as it is, it's not easy to see what kind of, how many of massless particles are there of this type. But you can actually write this as you can actually write this as A, I, J bar, K bar, A, epsilon, J bar, K bar, L bar, actually omega. And then G of J, L bar, where omega is the inverse of holomorphic threefolds. So remember that Calabi-Yau, on the Calabi-Yau manifold, one of the unique features of Calabi-Yau manifold is that there is this everywhere non-zero holomorphic threefolds. So that was the existence of that implied the Yau's theorem. Yau's proof of original Calabi conjecture is that if you have scalar manifold for which there is everywhere non-vanishing threefold, then there must be a rich flat scalar metric only. And so the basic assumption of Calabi-Yau, and Yau proves that such construction is possible. And so basic assumption is that there is such holomorphic threefold. So you can consider using the inverse of this to turn this single SU3 index to the pair of antisymmetric anti-holomorphic indices. Okay, so this is actually one two-form. Namely, there is a natural form which can be written as AI, J bar, K bar, A, dzi, dzj bar, dzk bar. So therefore, for each one of state configuration in the representation of 27 and 3, then you have actually this 1, 2, 4 on the Calabi-Yau manifold. The massless condition requires that this is closed and co-closed. Namely, the massless requires that A satisfies this equation, which is equivalent to say that dA is equal to 0 and dA star is equal to 0, and which is equivalent to say that A is an element of H21 of Calabi-Yau manifold. So therefore, the number of things, so therefore, the massless particle obeying 27.3 is equivalent to the element of H21 of Calabi-Yau manifold. Okay? Yes, please.
Question. So in 10 dimensions, the space-time index shouldn't it transform under the Lorentz group?
Yeah. So it's but we are considering here the counting chiral multiplet, which consists of scalar and chiral fermions. And so you are interested. You might be interested in first counting scalar, because if you count scalar, you can count fermions because they pair up. So you are interested in scalar, so that means that this vector pointing in 10 dimensions, among the vector pointing in 10 dimensions, the one that is relevant for this counting is the one that I point in the Calabi-Yau direction, so that it is scalar in the transverse direction. So therefore, I goes from 1 to 3. So that's why you have holomorphic index with 1, 2, 3, and then also another holomorphic index which comes from this internal gauge symmetry, and identified with space-time coordinate because of this identification that spin connection is gauge connection. So you have this combination, and in addition you have E6 27 representation. So for each one of them, there is an element of H21. That was what I showed here. And so therefore, if you count this, you can count number of them. So therefore, the number of massless particles in this representation is given by this Cauchy number. Okay, so now let's discuss the remaining two things. So how about 27 bar, 3 bar? So this also gives you n equal 1 chiral multiplet. But now you do the same exercise. So you start with in 10 dimension. You have a gauge field transforming in the adjoint. So that means that 248 of E8, and this is the space-time index. But just like before, we are interested in counting chiral multiplet. So therefore, you ask, well, how many of these are massless mode in 4 dimension when I goes into the internal Calabi-Yau direction? Okay. So now we are doing this decomposition. So that means that among them we are interested in finding this representation where this is the 27 bar and this is in 3 bar of E6, sorry, and then this is 3 bar of S23. Okay, so now this is easy because this goes from 1 to 3, this one goes from 1 to 3. So it is naturally correspond to A tilde, which is equal to A I J bar of A dz I dz J bar. And massless means that A tilde is equal to 0, which corresponds to D A tilde is equal to 0, and then D star A tilde is equal to 0. Actually, to be precise, this should be properly covariantized because these are gauge fields. But anyway, so this corresponds to the element of H11 of Calabi-Yau. So So now, so you see that the number of generation, number of multiplet in 27 representation is given by this Hodge number, and number of representation in this representation is given by Hodge number. So therefore, the number of representation in 27 bar is given by the Hodge number H11 of Calabi-Yau. Okay, so this is actually one of the most beautiful consequence of this paper by Candelas, Horowitz, and Strominger and Witter. Namely, that if you look at the massless vector, then you have adjoint vector field in 27, and they are super partners. So this gives rise to E6 gauge field. And then you can ask how many matter contents are there. So there are particles transforming in 27, and then there are particles transforming 27 bar. And so the number of particles transforming in 27 is H21, and number of particles transforming in 27 bar is H11. So you can ask how many. So in particular, the interesting invariant is the difference of 27 and 27 bar. Which is equal to H21 minus H11. And this turns out to be minus 1/2 of Euler characteristic of Calabi-Yau manifold. And the reason for that is the Hodge diamond of Calabi-Yau. Namely that as I mentioned, the Hodge diamond HPQ of Calabi-Yau is given by this 0, 0, 0, H11, 0, and 1, H21, H12, 1, H22, 0, 0, 0, 0, 1. And the Euler characteristic of Calabi-Yau is given by alternative sum of minus 1 of P plus Q of HPQ. And so this is 0, 0, this is 3, 0, 0, 3, 3, 3. So therefore these contribute to the Euler characteristic with plus 1, these contribute to minus 1, so they cancel. H11 and H22 are the same number by Hodge duality, and the 21 and 12 are the same. So that means that this is equal to twice of H11 minus H21. So this turned out to be equal, therefore, to minus of number of 27 plus, well, actually twice. So this is minus twice of number of 27 and minus of 27 bar. So this actually is a natural number for the number of generation in E8. So if you consider E8, so E6 grand unification, of the standard model, so standard model has this symmetry group SU3 cross SU2 cross U1. And this gauge symmetry is naturally embedded into E6. And the remarkable fact is that the quarks and the leptons, that quarks and electrons and neutrino, etc., transforms under certain representation of SU3 cross SU2 cross U1. And it turns out that they can be combined into 27 and 27 bar of E6. That, for example, if you have Yeah, so each representation can be combined into 27 and 27. But or stated in another way, if you start with 27 of E6, and then decompose that into representation of SU3 cross SU2 cross U1, then it gives rise to exactly the representation for which the quarks and the lepton belongs. So it's a natural grand unification of standard model where we unify the strong, weak, and electromagnetic forces. Now, if you have a generation of particles transforming in 27 and 27 bar, then generically you would expect that they actually give rise to mass term. Namely, that if you have a fermion in 27 and another fermions in 27 bar, you can actually write down the mass term, which is singlet under E6. So in particle physics, often, so and this is what Marie-Germain said, that whatever is not forbidden is mandatory. And so if symmetry allows you to have a mass term pairing up 27 bar, then generically you would expect that by dynamical effect the mass term will be generated. So therefore, it's very natural to expect that the actual number of generations that come from this type of construction is actually 27 minus 27 bar. So therefore, this is actually the most natural expectation for the number of generations you would obtain for this grand unification. And so I found it just very beautiful that this number of generation of standard model particles that that come from Calabi-Yau compactification is actually just given by this single number as an Euler characteristic. Okay, so that is one of that. So we have already explained the three parts of this decomposition. So this gives rise to the gauge field, and this gives rise to the matter content, which can be candidate for quark and lepton. For yes, we have a question.
What is this K of symmetry breaking from this E6 to the standard model?
Yeah, so this needs to be explained. So for that I need to explain the symmetry breaking mechanism, which I will come later. Okay. So far we learned on E6. Okay, so we need further mechanism of breaking this E6 symmetry down to this, and then I will give you some possible. I will explain some possible mechanism for doing this. Okay, so now the remaining thing is 1/8. So what is this 1/8? Okay, maybe I can. Okay, so what is 1/8? So this is singlet under E6 and is in adjoint representation of SU3. Okay, and in order to understand this low energy standard model physics construction, essentially, therefore, you can think of this as also part of the hidden sector because it is neutral under E6. So I said that in addition to this, there is another E8 in 10 dimension, and that gives rise to hidden sector seen from this E8, E6 grand unified model. So therefore, a candidate for dark matter. So this can also be part of that hidden sector. But this one is of slightly different nature for the following reason. So this comes from the 10-dimensional gauge multiplet, and this is 8. So what does it mean? So actually, the explanation of this is the following. So first of all, as I said, as I explained, this 3 was explained, this 27 and 3 was explained as an element of H21 cohomology. And this 3 bar was identified with H11 cohomology. Similarly, this 8 can be interpreted as H1 of endomorphism of tangent space. So let me explain what this concept means. So it is the following things. So so remember that when we solved dH is equal to 4 alpha prime trace R wedge R minus trace of F wedge F, we set H is equal to 0 and omega is equal to A. And this was a nice class of solution. Of course, this solves this equation. Left hand side is equal to 0 and right hand side is equal to 0, so this is solved. But this was a special class of solution. This is a nice class of solution because on the worksheet in the NSR formalism, it has supersymmetry for the both left mover and right mover of the worksheet. And but a priori, there are more solutions. So you can ask, are there ways to deform this solution that still remains a solution? Okay, and there is such a possibility. And one possibility is still maintain H equals 0, but deform this condition so that the condition that R wedge R minus trace F wedge F is still satisfied. And you can use this, you can do this if you can deform A. So you can deform A, So originally A was equal to omega. But you can deform A from omega, provided that the corresponding gauge field continue to satisfy the Uhlenbeck-Yau condition. So provided that this equation is satisfied, then you can actually deform this away from this. Because this equation guarantees that the value of f is not deformed away from this. Okay? So therefore, you can ask, well, what are the class of solutions, deformation of this equation? Well, it's easy to see because suppose you start with a solution satisfying this condition. And then suppose you deform it away from this, then the deformation would satisfy this condition. Right? This is exactly what this 8 means. Because Fij has 9 indices. Because I go from 1 to 3, and J bar go from 1 to 3. So there are 9 of them. And we impose one condition, which is a traceless condition, which is exactly the condition for the adjoint representation. Because the adjoint of SU3 is generated by 3 by 3 Hermitian matrix, which is traceless, which is exactly this equation. So actually there is one-to-one correspondence between this 8 direction and this direction. And this is essentially what this notation means. So you can think of, therefore, this corresponding to the deformation class of this equation. Now, sometimes actually there is an obstruction to deform this equation, and that corresponds to the situation where the massless particle for the massless particle corresponding to this direction, it turns out that if you actually take into account some various non-perturbative effect, it gives rise to some potential. So therefore, the expectation value of this field is fixed. And in some cases, there are flat potential. So these are actually more subtle questions. And this is related to the subtlety in studying what I call the 2-0 compactification. So therefore, the massless particle would be massless particle belonging to this representation. Describes the deformation class of string compactification from 2-2 to 2-0. Okay, so that's the interpretation of this. But anyway, so this is an interesting class of particles, but these are neutral with respect to E6. So from the point of view of particle physics model building, you can think of that as part of the hidden sector. Depending on whether potential for this direction get developed, this class of particle can be either massless or massive. Yes, you have a question.
Can I think of this as a deformation of the complex structure on the target space?
No. So deformation of the complex structure in Calabi-Yau is described actually by this one. And this corresponds to the deformation of Euler structure. This is actually deformation of Yang-Mills bundle on the Calabi-Yau manifold. Okay, so there are three deformations because we are considering Calabi-Yau compactification and then E8 gauge field on the Calabi-Yau manifold. So therefore, you can deform the base Calabi-Yau manifold, and by the Yau's theorem of Calabi conjecture, there are two deformation classes. One is complex structure deformation of Calabi-Yau, and another is a Euler class. And that is because Yau's theorem guarantees that for each choice of complex structure and Euler class, there is a unique rich flat Euler metric. So this parameterizes the deformation of the base Calabi-Yau manifold. But for each given Calabi-Yau, you still have a choice of gauge field on the Calabi-Yau manifold. The gauge field has to satisfy Uhlenbeck-Yau equation. And then you ask, what is the deformation class of Uhlenbeck-Yau equation? And that is given by this. And that is what this means. Okay? I hope that's clear. Okay. All right. So we are almost done, except that we would eventually like to break E6 down to SU3 cross SU2 cross U1. So giving rise to the actual standard model of particle physics. And there are ways to do it. There are a variety of ways to break this symmetry. One natural way of doing it is called homotopic mechanism. So this is actually the string theory version of the Higgs mechanism. So Higgs mechanism calls for some massless particle, massless scalar particle, which develop expectation value and breaks part of the which transforms non-trivially under symmetry and breaks symmetry. So there is a stringy version of this in the following sense. So suppose Calabi-Yau manifold has a non-trivial fundamental group. The pi1 of Calabi-Yau. By this I mean the following. So let me draw some picture. So suppose, for example, you have a torus. Then there are two generators of fundamental groups. So you can go around here, come back, or you can go around here and come back. In general, the fundamental group can be defined as a deformation class of a loop starting from some point on the manifold, go around and come back. Exactly. And you consider path. And then you consider what's called the homotopy class of the path. So you allow continuous deformation of the path like that. And then if you consider homotopy class, of gamma, then it gives rise to a group. And it's called fundamental group. It's pi1 of the manifold. And it's natural. It's very natural. For example, if you in order to be a group, you have to be able to multiply them, and of course you can multiply them because if you have two passes, gamma 1 and gamma 2, then you can multiply them by first going around it and then going around it second time. Okay. And you can also have an inverse because you can go around in one path, and you can go back around the homotopically equivalent path, and that be an inverse. And you can show that this satisfies associativity. So it gives rise to a group. Under homology, unlike homology group, in general, pi1 can be non-abelian. So for example, there can be elements that do not commute with each other. You can easily construct it, so like for example, in the fourth floor. So the fourth floor, there are lots of columns. So there are open space, but there are columns. and there are actually islands of offices in it. If there is only one column in a single room, then homotopy class is Z, the integer. So it's abelian. But you can easily test yourself by going upstairs on the fourth floor that the homotopy class of the fourth floor is non-abelian. So you can think what kind of group that is for a homotopy class of the fundamental group of fourth floor. Well, that I will leave it for your exercise. But anyway, so for each, there are manifolds for which fundamental group is non-trivial. So suppose you have a non-trivial fundamental group. So there is a path for which you cannot contract. So if you have a non-contractable group, then you can consider what's called the Wilson line or the holonomy of the gauge field. So you have the E6 gauge field on Calabi-Yau manifold, and so this you can think of as part of this thing, this fellow. But now the vector is pointing in the inside of Calabi-Yau, not outside. And if I is pointing in the direction of internal space, then in general it does not give rise to massless particle by itself, because in general H10 is trivial. But even if H10 is trivial, there can still be non-trivial element of the fundamental group, and you can actually construct example of Calabi-Yau manifold for which it is possible. And if you have that, then you can actually give rise to the Wilson line in some particular representation R, which I define as path ordered exponential trace of path ordered exponential of the gauge field around gamma and in the representation R. So let me explain what I mean by this. So what does a path ordered exponential means? Well, of course, if you have exponential, it is 1 plus a plus half of a square plus etc. And now we want to first consider integral of gauge field around the path. Now, if the gauge field is abelian, then we don't have to worry about the order of the path. But if A is not abelian, it's not abelian if it is no abelian gauge field, like in the case of E6, they don't commute with each other, so we have to worry about how to order them. So there is a natural order called the path order, which is, so if you have path order exponential of IA integrated over gamma, what I mean is the following. So we have 1 plus contour integral of A plus 1/2 of minus I squared, so that is equal to -1, minus 1/2 of integral of A and integral of A plus, minus 1/6 of I of integral of A, integral of A, integral of A, right? So it goes like that. And path order means that, for example, if you have 2 of them, so you have this path, gamma, and then the A is integrated over here, and the other A is integrated over here, and you position these 2 A's anywhere around gamma. So when you do this integral, what you do is to place A, which is the later in A, to be on the left side, and then so you order this A, you position A in this integrand in a way that respects the order. So that's called path order. Okay, so it's actually simple algebra to show that if there is a path which goes from the point P to point Q. So let's call this as path gamma PQ. If you have a path which goes from point P to point Q, and if you consider path order the exponential of gauge field which goes from P to Q, like this. Okay, so if you consider this kind of path order the exponential, and suppose you do the gauge transformation, which transforms gauge field A to be omega A omega inverse plus omega of D of omega inverse. So suppose you do this type of gauge transformation, then you can show by simple algebra that this path order exponential of this integral from P to Q of A transforms into omega. So let me make sure that order is correct. So it comes over here. So I think it comes to P of path order the exponential of I integrated of P of Q of A and omega inverse of P. So you can check by yourself relatively easily that if you do this gauge transformation for omega in the gauge group, then this path order exponential transforms in this way. Okay? So this is gauge covariant. And in general, if you don't do path order exponential, then this gauge group factor got mixed up and it doesn't transform nicely like that. But if you do path order exponential, it gives rise to this. So then pick any representation. So let's call that R of G. And evaluate this path order exponential. So this is an element of gauge group G. So you can evaluate that in any representation and take trace in that representation. Take trace in that representation. And then path order the exponential of I. Now integrate over closed path of A. If you integrate gauge field over closed path, the P and Q are the same. So closed path means that the P is equal to Q. So that means that you have same omega sitting here, omega and omega inverse. So if you take trace, they get cancelled. So that means that this is gauge invariant. So for gauge theory, this is actually a very nice class of observable that is gauge invariant. And this is called Wilson. Ken Wilson was a grad student at Caltech, and one of the things he was interested in was to understand quark confinement. So why quark and antiquark get confined and we cannot observe them in nature. And one of the ways that he considered in identifying in which situation quark confined is to study the property of particular type of observable called Wilson loop. So this is the observable in gauge theory that he defined in order to diagnose whether quark gets confined or not. So he showed that depending on how the expectation value of the Wilson loop behaves, you can diagnose whether in particular gauge theory quark gets confined or not. Okay, so this was a very important insight. And for a heterotic string compactified on Calabi-Yau manifold, we can also consider Wilson loop for the E6 gauge field. And so why this is interesting? Well, because if this Wilson loop gets some expectation value, then since it's transformed under E6, so therefore I can break E6 further. So therefore, having this Wilson loop potentially have a way to break the gauge symmetry further, and so this is one of the scenarios that being considered to have to realize the standard model of particle physics. So to summarize, the construction we considered is start from E8 cross E8 heterotic string, and then compactify it on R3, 1 times the Calabi-Yau manifold. And on Calabi-Yau, we do two things. One is omega is equal to A, which gives rise to 2 compactification. And then from this compactification, the E8 248, I suppose, get decomposed into not this one. 78,1, which is which gives rise to E6 gauge view, plus 27,3, which is chiral fermion, and then 27,3. So this is the generation of quarks and leptons, and these are anti-generations. And then plus 1,8, and this is possible to deform to compactification, to 0 compactification. And then, so this gives rise to E6 ground unification with number of generation given by absolute value of H11 minus H21, which is 1/2 of absolute value of Euler characteristic. Okay? And I put absolute value because whether you call this as generation or whether this call it as generation and the other one to be anti-generation is a matter of convention. So we can put whichever larger as we can call whichever larger as generation and the other one to anti-generation. And then the difference, the one that if you have same number of generation and anti-generation, they can pair out to become massive in general by Gelman's principle that everything that is not forbidden should be mandatory. And so therefore this is a natural quantity of the number of generation. And this E6 can be broken further to SU3 cross SU3, SU2 cross U1 by turning on the Wilson line. If the Calabi-Yau has non-trivial fundamental group. So this is sort of one of the scenarios which give rise to the standard model of particle physics. This was the first example proposed in the 1984 paper by Candelas and collaborators. And so this became sort of a prototype of how possibly standard model can arise from string theory construction. Now there are many other construction and which can lead to also standard model. And one of the another promising direction is to make use of D-branes and orientable, which I will discuss next. Okay, but any questions so far? Over here.
I am having trouble seeing how turning on the Wilson lines would
Beg your pardon?
How does turning on the Wilson line break the gauge symmetry?
Because so if this gets the expectation value, then that means that there are some particular direction of gauge field which has non-zero expectation value, and that breaks symmetry. Okay, so now let's change the subject a little bit and then start discussing D-brane. So let me first motivate the introduction of D-branes. So deep brain has interesting history. So people know about open string, and if you have T-duality transformation, which relate torus of certain radius to torus of the inverse radius in a mechanism that we discussed earlier, then it gives rise to open string with a combination of Dirichlet and Neumann conditions. So those things were known already in late 80s by Polchinski and others. But identification of these as objects carrying Ramon-Ramon charges was not realized until mid 1990s. And but let me do not respect the history and explain this in a sort of more fundamental way. So I would like to discuss deep brains. So I think the fundamental motivation for deep brains is that string theory has lots of unsymmetric gauge field, and it's natural to consider objects which are charged with respect to this gauge field. So for example, if you consider type 2A or 2B theory, then on the string worldsheet, you have coupling of worldsheet coordinate to the metric, but you also have coupling to unsymmetric tensor field. So of course G mu nu is a metric, and then B mu nu is unsymmetric. So it satisfies B mu is equal to minus B mu. Okay? And then plus terms that contains fermions. So therefore you already have B field, and then there is a gauge symmetry, which B field transforms like that. The reasons for that is that under this transformation, the worldsheet action gets total derivative term added to it, and so therefore the action is not modified if you are considering closed string. So this is a gauge symmetry of the B field. So and then therefore the field strength is H mu nu rho, which is totally unsymmetric version of B field. And this was what was used to the analysis of Calabi-Yau compactification. So this is in the NS sector, but so this is this B field is in the NS sector. But if you remember our discussion, there are also unsymmetric tensor fields. In the Ramon field, Ramon sector. And there are many of them. And the way it appears is the following. So if you remember this type 2 string construction, in Ramon sector, in NS sector, left mover gives you a vector and right mover gives you a vector. So massless sector of Ramon sector is a bivector. So if you have a bivector, you can decompose that into symmetric part and unsymmetric part and trace part. And they can be identified with graviton and the unsymmetric tensor and Dirac. So there are three types of massless particles correspond to decomposition of the bivector. The Ramon sector, the ground state massless ground state states are spinors. So therefore, the ground state, the massless sector, are bispinor. So here you had the bivector, pair of vectors that can be symmetric, unsymmetric, or trace. Here is a bispinor. So you can think of any field in this sector as some F with the spinor index. But spinor can be either chiral or antichiral, which I may put dot over there. So it can be F alpha beta dot. Okay, remember that so far we are in 10 dimension. So let me stick to 10 dimension for now. And in 10 dimension, one of the important features of 10 dimensional Minkowski space is that you can have Majorana wire spinor. So namely, the spinor can be satisfy both wire condition, which means that you can have a notion of chirality for fermions, but you can also define reality conditions, which is called the Majorana condition. So these are Majorana wire spinors, and there's a pair, and that gives rise to the massless particle. So in type 2A, the Ramon sector in type 2A theory is bispinor but with opposite chirality. That was due to this GSO projection that we talked about. So if you have a bispinor of this, then you can show that they can be decomposed into they can be please excuse me. So they can be decomposed into field strength, which is a scalar, unsymmetric tensor, and then the 4-form and 6-form. So I ran out of indices, so let me parameterize it in a different way. C mu1, mu2, C mu1, mu2, mu3, mu4, C mu1, mu2, mu3, mu4, mu5, mu6, and C mu1 to C mu8, and then 10. Okay, so there are those things, but there is also duality symmetries which relate the P form into 10 minus P form. So these can pair up, these can pair up, and these can pair up. So another way of writing it is that there is a 0 form, 2 form, 4 form, 6 form, 8 form, and 10 form, but C of n is a dual of C of 10 minus 10. Okay, so there are these unsymmetric tensors, and they all satisfy the equation that dCn is equal to 0 and d star of C of n is equal to 0. So that means that there is n minus 1 vector field from which Cn can be written as C of dn minus 1. Okay, so this is type 2A theory. So type 2B, you have spinors, bispinor of the same chirality. So this gives rise to C1, C3, C5, and C7, and C9. Okay? So, and then again they are paired up. So this is paired up with this one. This is paired up with this one. But interestingly, C5 is self-dual. So this gives rise to this self-duality of 5 form, gives rise to all interesting features of type 2 B string theory. One of the significant features is that type 2B string is self-dual. That the strong coupling limit of type 2B string is actually weak coupling limit. of type 2B string itself. So anyway, so you have all these kind of forms, and then naturally, therefore again, this n form in type 2B theory associated to n form in type 2B theory, there is a corresponding n-1 form potential. Okay? Now there are so many of gauge field, and you can ask, are there objects in this string theory which carries charges with respect to this gauge field? So whenever you have gauge field, it's natural to have object. It can be particle, or it can be some string or extended object which carries charges. Well, the purpose of life of gauge field is mediate force between object. So if there are no object charged with respect to this gauge symmetry, then the gauge field loses purpose of life, and that's very sad. So we would like to help them avoid that. But in fact, this is actually one of the principles of quantum gravity. That in the context of ADS-CFT correspondence, which I hope we'll have time to come to, actually Daniel Harrow and I proved about 7 years ago that whenever there is a gauge symmetry in quantum gravity in unit space, then there must be object that's a charge with respect to this gauge symmetry. So in the case of ADS gravity, this actually is a fundamental principle. We don't have the proof of that statement for quantum gravity flat space. So my proof with Daniel Harrow applies to any quantum gravity theory. So it can be string theory, or it can be some other theories that I do not know whether such construction exists. But whatever theory that you succeed in formulating in isolated space, then in such quantum gravity theory, for every gauge symmetry, there must be charged objects.
Question.
Yes?
Do you think completeness has to be a holographic state function?
So what I said is that if you assume ADS-CFT, this is a theory. That's all I can say. Okay. So in string theory, we have all these gauge fields. So it's natural to postulate that there must be charged objects. But it was sort of puzzling, because for many years people didn't find such charged objects. For the unsymmetric tensor field in a sector, there is a charged object, and that is actually a string, because this gives rise to a coupling of string to the B field. So this is actually very natural generalization of what we know about the electrons. So you know electrons are charged, and the electrons are charged with respect to Maxwell field, right? So electron carries a charge with respect to the Maxwell field. So Maxwell field, the gauge potential for the Maxwell theory is a one form. So being one form, what happens is that if you have electron moving in space-time under some trajectory, then you can actually naturally define this object. So this electric charge with gauge field integrated over the path. You might recognize this takes exactly the form of Wilson loop. So in fact, Wilson loop was inspired by this kind of things. And in the case of Maxwell theory, it's abelian, so we don't have to do path ordering. If this was the SU2 or SU3 gauge group for fundamental standard model of particle physics, we will have to do path order exponential. But for electrons, we can do this. And so what we saw over here is a natural generalization, because the fundamental string carries a charge with respect to the B field. And the proof of this is here, namely that if you have Lagrangian density like that, then action is I times exponential of integral of that, and then it's actually coupled to the string wall sheet in this way. So and then this sigma is a trajectory of string. So you see that this is a natural generalization of electron phase factor associated to the propagation of electron in the gauge field configuration. Okay, so for this NS-NS2 form gauge field, there is a natural charged object. So the question is that what are the objects in string theory for which are charged with respect to all these? And the D-branes and orient fold give us the answer to this question, which I will discuss in next week.